Acceleration is especially worth focusing on, as it describes how a curve's tangent behavior evolves over time. So let's think more deeply about acceleration and the acceleration vector, which has both a magnitude and a direction. What do these mean? Well, let's say we're given a parametrized curve in Rn. Call it gamma. It's a function of some parameter. Let's say t, time. Then velocity, v of t, and acceleration, a of t, are often expressed or described in terms of a pair of orthogonal unit vectors for each time t. So think about it this way. You pick a point on the curve, that's some time t, and you've got the velocity vector, which is pointed in a direction tangent to the curve. The acceleration vector at that time is not necessarily pointed in the same direction. The two of them together span a plane. How are we going to describe that? Consider t, the unit tangent vector at time little t, and this is the vector that points in the direction of v but has unit length. And now we're going to consider a vector orthogonal to that called the unit normal vector, denoted capital N, and this points in a direction that is orthogonal to the unit tangent vector, but together which span the plane that the acceleration and the velocity vector are in. So again, this normal vector n satisfies the definition that n dot t equals 0, but more precisely, that unit normal vector is defined in terms of the derivative of that tangent vector with respect to t. So you take that derivative and then you normalize it. You divide by the length of the derivative so that you get a unit vector. Let's see how that works in a particular example where I give you the position vector of a curve. So r of t is cosine 3t, 4t minus 1, sine 3t. This particular type of curve is really interesting. It's called a helix, and this helix is opening up along the y-axis. Computing the velocity by taking derivatives yields negative 3 sine 3t, 4, and 3 cosine 3t. Computing one more derivative is going to give us the acceleration vector for this helix. This is going to have components minus 9 cosine 3t, 0, and negative 9 sine 3t. Now, to compute the unit tangent vector, what do? We take the velocity vector and we normalize. We divide it by its length, that is, divide by the speed. Now, in this case, if you do a little bit of math off to the side, take the square root of the sums of the squares of the terms, you see a wonderful simplification. You'll see a little 3, 4, 5 action going on here, and what you'll get is that the speed of this curve is a constant. It's equal to 5. Okay, now to determine the unit normal vector, what do? We have to differentiate this unit tangent vector with respect to t. That's not so bad. It's going to give me a cosine term, and then a 0, and then a sine term. Then we have to normalize. That is, divide out by the length of this thing, which is some big ugly square root. Oh gosh, I don't want to deal with that. I'm just going to put a smiley down there. Oh, but wait a second. Oh, that's maybe not going to be so bad. Why? Because I've got a cosine of something and a 0 and a sine of something. And so when I square those and add them together, well, look, it's just going to give me a 9 there. And normalizing by that gives me a unit normal vector with components negative cosine 3t, 0, and negative sine 3t. And I look at this and I say, oh, wait a minute, aha, I see that this unit normal vector is in fact parallel to the acceleration vector. Now that's interesting because it's orthogonal to the unit tangent vector. And what this means is that this curve has no tangential acceleration. All the acceleration is happening in the normal direction, in the direction orthogonal to velocity. And this really makes sense. Why? Because the speed along this curve was constant. Okay, now in general, what one does is decomposes the acceleration vector into a tangential and a normal component. It's not always the case that the acceleration is orthogonal to the velocity or tangent to the velocity. Most times, it's a mix between the two. So how do we get that decomposition? Why do we want that? Oh, this is very useful in many physics contexts. The tangential component of acceleration, denoted a sub t, and the normal component of acceleration, denoted a sub n, tell you things about rates of change of speed and about how the curve is bending away. Now, here's a fact. The tangential component of the acceleration is the derivative of the speed. And the normal component of the acceleration is proportional to the square of the speed, where this constant of proportionality is denoted kappa, and it's an interesting constant. We're going to take a look at that.